Okay, good afternoon, good morning to Canada. It is my pleasure to introduce Professor Thomas Hillen, whose research area is in mathematical biology, where he has a good number of reference papers in different fields. To name a few, for example, his collaboration with Professor Ottmer on diffusive limits, or with Professor Painter on a user guide of on chemiotaxis. This paper, for example, have more than 1,000 citations, or also with Professor Painter on the influence of the fiber structure by means of diffusion tensor imaging in the direction of migration of glioblastomas. For example, is also one of the reference paper among many other papers. His current research focuses on the analysis of transport equation, in particular reaction diffusion or advection diffusion equation, and their application to chemiotaxis. In general, the migration of cancer cell in tissues, or more general spatial patterns generated by partial differential equation. Today, he will speak about mathematical modeling of metastasis. Thank you very much to accept our invitation. It's a pleasure to come with you in this series of seminars.
Yeah, Juan and all the organizers, thank you very much for giving me a chance to talk here. I have been to all the other talks and I thought they were really, really good. This seminar is really run very well. And it's a great honor to be also able to speak here. I like to talk about metastasis, so nothing about chemotaxis, but about metastasis. And this is joint work with Adam. I'll just get my pointer organized. Yeah, here we go. So this is Adam Rhodes. Adam is a PhD student of mine, and Chris Fry, he is a colleague in my department. So let me tell you what I have in mind with metastasis. I think most of you know, no, all of you know, metastasis is a very serious thing related to cancer. It often is observed at the very end of the disease, and about 90% of cancer deaths involve metastasis in some form or the other. And of course, that's why it's very important for a cancer patient to make sure there are none. So metastasis observation is taken very seriously for all these cancer patients. Still, the mechanism for metastasis is relatively poorly understood. There are certain aspects which are really well understood, and I talk about those, but there are other aspects which are actually not understood at all. And I think, tada, this is an opportunity for mathematical modeling. Because I think one strength of math is to be able to analyze complex systems and complex things, and metastasis is certainly something very complex. Okay, so here's a predominant picture how metastasis work. It's called the metastatic cascade. And let's talk about these steps here first. So everything starts with a primary tumor sitting in some tissue here. And then often you observe local invasion. And this is when cells transform from a epithelial type to a mesenchymal type, and they become invasive, they lose adhesion, and then they invade into the local tissue. And then while doing this, then they can eventually reach a blood vessel right here, and then intravasate into the blood. And of course, if the cancer is vascularized already, then they don't have to go, then they have access to the blood vessels immediately. Then during the blood system, they're transported through the entire body, and they form microclusters, what are they called? Cancer cell clusters. And in the blood, they have a very hard time to survive. So the survival of these shedded cancer cells in the blood is actually rather low. But still, some survive. And then there are two ways how they can form metastasis. One is they get stuck, which is indicated here. If the capillaries become too small, then these clusters just get stuck, and that's it. And then they can still grow. Or they actively extravasate. Maybe they find the liver, they like the liver, there's lots of alcohol there, so then they go and hang out in a new organ. And then if the conditions are right, they can form micrometastasis first and then larger metastasis later. So what I have in mind is in this talk are two things. Yeah, one is a question, where do they go? So this process of shedding, transport through the blood system, and then extravasation. And this is, of course, a highly stochastic thing. You can really not predict where they will end up. And so we derive a stochastic model for that process. And then the second thing is, which is not included here in this image, is the role of the immune system. So then in the second part of my talk, I look at the role of the immune system in the growth of the metastatic colony. Okay. If you look at medical literature about metastases, there are some very interesting curiosities related to these. So first of all, metastases often go to bone, lung, and liver. In particular, prostate cancer goes to the bone almost every time when it's really, really bad. The question is why? Why is it found in these organs predominantly and maybe not so much in other organs? Another effect is dormancy. So it has been found now that metastases can actually form quite early in the disease and then just sit there and do nothing. And only after a while, nobody really knows, or actually some reasons are known, but not always, then they come. All of a sudden they come and grow. And so they can lie dormant for a long time. It's not very clear why this is the case. One of these instances is the removal of the primary tumor. In many cases, once the primary tumor is removed, then all of a sudden the metastases start to grow. And this is called metastatic blow-up. And again, it's a question, what is the communication between the primary and the metastatic tumor? Once you remove the primary, then the metastases blow. Another interesting fact is metastases occur at sites of injuries. So there are reports, for example, when cancer patients have a dental procedure, dental surgery, that then right at the dental surgery wound, you observe a metastasis formation. So the wound doesn't heal, it rather forms a source or a niche for metastasis formation. And this has been observed in other contexts where people have broken bones to an accident, say, or skiing or something, and then they form cancer right there. And then the doctors actually look for a primary tumor somewhere else in the body, which might be the cause. Metastases relate to chronic inflammations for patients who have chronic inflammations. And then also metastases, of course, play a role in immunotherapies because in particular immunotherapies are meant to find all cancer cells, no matter where they are hiding. And this works sometimes, but sometimes it doesn't. And so these three questions are kind of the guiding questions through this talk. And then in particular, the last three here, these ones, they have all to do with the immune system. Right, injuries, inflammations, and so on. This has to do with a very active role of the immune system. And I like to analyze this a bit more. So before I do this, let me look at the previous literature a little bit. I'm not going to talk about all these papers, but I highlight a few. And maybe I show them first all. So for example, well, there's a class of stochastic models, which, I mean, makes a lot of sense. It's a stochastic process. You don't know where they go. So stochastic model is the first idea you should have. And then there is a work by Hanin from 2006. This is a little typo, to 2018, about the natural history of metastasis. So he looks at the size distribution of metastasis. He doesn't look where they go. He just looks at the size. How many do you get of which size? And he finds that they actually arise early in the disease. So even if you see them later at the end, they might actually be there for years and years earlier. And that's a very serious find. And then the work with Fry, Hillen, Rhodes, this is what I'm going to talk about in a few moments. And then down here, there are several models which include the immune system. Maybe I highlight the work of Friedman, Avner Friedman, the famous PDE guy in Minnesota, Raluca Eftimi, on M1, M2 macrophages. M1, M2 macrophages are part of the immune system. And it has been shown that they can arise in two forms. M1 kills cancer and M2 helps cancer. And so there's an interesting feedback between these types of immune cells. Yeah, actually, in this context, I would actually recommend if you have a next round of your seminar, you might want to consider inviting Raluca Eftimi. She's, I think, now in Grenoble. She would be an excellent speaker. Okay. So what am I planning to do? The one is the question, where do they go? And for this, I develop. Is there a question?
It's in Besançon, not in Grenoble now, I think.
Oh, Besançon. I'm sorry. Thank you. Okay.
We are in contact with
her. So where do they go? And for this, I develop a branching process with settlement, which then leads me to the derivation of a metastatic reproduction number, which is a very interesting observation there. And then secondly is how do they grow? And this is where I then wonder about the role of the immune system in the growth of metastasis. So we call it the immune-mediated theory of metastasis. All right, let's start with the first one, branching process with settlement. So now the idea is you have a primary tumor somewhere, it is shedding particles into the bloodstream. And the bloodstream circulates it through the entire body. So the circulation time is about 8 minutes. Within 8 minutes, it has reached everything in the body. So on the time scale of cancer growth, this is super short. That's basically instantaneous. So we look at the primary particle located at axis 0. That's the primary tumor. Then we look at shedding. So at a random time, which is exponentially distributed, it sheds a particle, which then moves around randomly. And the movement is described by a spatial random process B. Of course, we want to use blood. That's why we use a B, but then in examples, we often use Brownian motion just because it's easier to work with. At a random travel time, it settles down somewhere. And then the process can repeat. So then the settled particle can become a metastasis and then shed other particles in the system, and then the whole dynamics repeats. Moving particles can die with the rate delta 1, and then stationary particles can also die with the rate delta 2. So lots of text here. Let me show you this in a simulation. It's a stochastic process. So here's a primary particle located at 0, and it lives only until here, and then actually it has died. So the primary tumor can also die. But then at this time around 2, it sheds a particle, which then does a random motion. Here it's Brownian motion, settles somewhere, and then can shed another particle later, which is the purple one, which then starts another random motion. In the meantime, the first particle could have released another one, which then actually died over here. So that's the stochastic process we like to study. Let's introduce a few stochastic notations here. So n is the number of particles born before time t, xi is the position of the particle, and m is the number of particles alive at time t. And of course, this is the most important quantity, m. We would like to get m to 0, right? And then based on the stochastic process I defined earlier, we can derive expressions for these things, for these, So we have the expected location E, expected location F, which is the expectation to find the particle less or equal x. And this less or equal could be understood in a higher dimensional sense as well. The local variance, the variance of F, so the locational variance, the distribution of the furthest particle, the probability that the maximum of the xi is less or equal x, and then the survival probability, which is most important to us. This is now the survival of the metastasis, not the survival of the patient. So it's a survival probability of the metastasis. And it turns out if we do these macroscopic calculations, we find a very typical equation which holds for all 4 of these. So all 4 of these quantities satisfy more or less the same equation, which is given here. So if we take little f to be any of these location, variance of the location, furthest particle, or survival probability, any of these f satisfies an integral differential equation of this sort. where you have a decay term here, you have a growth term there, and then you have a non-local term which involves a convolution here. And then some quantities depend on space and time, so then the convolution is in space and time. The Q thing here depends only on time, so then the convolution is only on time. But still, the type of equation is actually the same, which is really interesting and quite unexpected, what we had here. Okay, so then we looked at this model, and so we could show positivity, existence, uniqueness of mild solutions, and then also H and Q are globally bounded by 1. And this last item here, I'm sure, well, I found this an interesting question, and I'm sure the PDE guys in the audience will find this interesting too, because my collaborator Chris said, Q, for example, the survival probability has to be bounded by 1 because it comes from a stochastic process. It has to be bounded by 1 because it's from a stochastic process. And I said, no, the PDE, or actually the non-local integral differential equation here, doesn't know that it comes from a stochastic process. It's just a differential equation, and we have to prove that Q is less or equal 1. And so we had a long discussion if this actually needs to be proven or if this would be automatic because it comes from a stochastic process. So anyways, we did prove it then in the end. Well, if it would not be true, then the model would not be good. That's for sure. Okay. Now, now we have this model, so we can analyze it further. And in particular, looking at the number of metastatic particles, M, we can divide them up into 2 bits, into the moving bit and the stationary bit, A and B. So the expectation of M is an A plus B, and this trickles down to a very simple 2-dimensional ODE. So then A prime, B prime, it's a linear ODE with all these rates, which I have defined earlier. And here they mentioned again. I will talk about the rates in a second. But of course, now analyzing linear ODEs is things we can do really well. And so we can define something like a reproduction number, R0, based on these parameters. And if R0 is less than 1, then the metastases die out. If R0 is equal to 1, they persist. And if R0 is bigger than 1, then they grow. Okay, so that's really interesting. So this was done for the ODE, but then the similar results holds for the non-local model if you apply it to the survival probability Q. And then we also get conditions where then the survival probability of metastasis, for example, is 0 under these conditions, or it converges to a maximum value here, or even to 1, which is a bad situation for these parameter choices. Okay. And this is exactly what we are after. So the R0 here is the interesting bit. Let me show you a simulation first. So here we run a simulation where R0 is 5. And then you see you get a very quickly population of the metastasis in this domain here. Right. Here is a simulation where we compute the expectation M of t, which is equal to A plus B. And we do the average over 2,250 simulations from a stochastic process, and we get a very good overlap also numerically of these two terms. Okay, so then what do I want to do next? Let's have a look at the terms, what they mean. So the first term, lambda over delta plus lambda, this is the odds of a moving particle to settle before it dies. So lambda is the settlement rate, delta 1 is the death rate. So then these are the odds to settle before something dies. And this term, mu over delta 2, is the ratio of the shedding over dying for the moving particles. No, for the stationary particles, sorry. Then if you want to use it for treatment, of course, you can either increase lambda you can decrease lambda, you increase deltas, you decrease mu. So what does this mean? You can increase delta 1 by boosting the immune system or using anticoagulants or using platelet inhibitors. So delta 1 is the survival during travel. And so you would try to do something in the blood system to so they survive less. And then delta 2 is the survival of the stationary particles, and this can be done through traditional treatment. If you know where they are, you can apply radiation treatment. If you don't know where they are, you can still use chemotherapy or other therapies. Decrease the shedding rate, mu. I have no idea how this could be done. And then decrease the settlement rate is to make it less likely for them to settle somewhere, and there are various methods. A simple method is by Bob Gartenby, just to make the body more basic, reducing pH level, increasing pH level. Okay, now I'm losing my chemistry here, right? Increasing means more basic. For example, giving the patient baking soda, and this could prevent formation or reduce formation of metastasis. But of course, nobody can make money, no pharmacy company can make money by selling baking soda, so they want to do complicated therapies like immunotherapies or other things to prevent premetastatic niches. But so I think this little simple formula actually can give a very good guideline of what treatment should look for. It also tells you that if you reduce 90% of the tumor mass without changing R0, then not much is gained, right? You delay the disease, but it will grow the same way as it did before. Okay. Now, as a final step for this bit, we fit it to real experimental data. And of course, where to look for metastasis data is mice. There are lots of mice experiments done for metastasis. And so here we have the shedding rate, the settlement rate, the mobile death rate, the stationary death rate. All this can be found in the literature. And so we can compute R0. And now let's compute R0. So in this case, R0 is 4.94, 10 to the 6. So it's 500,000. So yeah, you see me smiling here. So the poor mice, right? I mean, R0, 500,000, this means metastasis form with certainty over a very short time. But of course, that's the point of mice experiment, right? If you want to do a metastatic experiment on a mouse, you make sure they develop these in a short time because everything is expensive. So this is certainly far away from a typical human situation. But yeah, but that's what it is for mice. And then here, I show you the spatial distribution of the metastasis formation. So maybe in this graph here, at 0 is a primary tumor, and then using Brownian motion, then you get this kind of distribution near the release site of the metastasis. Again, right, this is based on Brownian motion. So this is what you expect. If we use blood circulation models, which actually exist in pharmacology, then you would, of course, get a very different distribution. But we have not done that. All right. So then let me talk about the second bit. So now I like to include the immune system into the mix. So again, we have a primary tumor here. We have a secondary tumor here. They're connected to the blood circulation, similar as before. But now what is new is the immune cells here. And so we have these immune cells with this chemical symbol there. They're cytotoxic. So they would kill the cancer cells. And then we have this symbol with the PhD hat. We call them educated immune cells, and they help the cancer. So what has been observed, and I show you papers in a second, that the immune system can actually play two roles. It can be cancer promoting and cancer inhibiting. And there's a transition from one stage to the other. And of course, the immune cells then also communicate to the blood system. So the educated immune cells, they can be transported to the metastatic site and then also help the cancer to grow here. And if this happens, you're really in trouble. This is not good. So let's look at the evidence of this idea. I got this idea in 2015 when I had a conference at the MBI in Ohio, and I met Laili Shahriari. She's professor at Amherst, and she read lots of papers on metastasis and wanted to do some modeling. And she found that in many instances, the role of the immune system is mentioned, and actually that the inflammatory process adapts immune cells in the sense that they help the cancer. So this got me really interested, and I thought this is a very crazy idea. But then there's more evidence. For example, here, this is already a paper from 2005, where they look at a piece of tissue, and then in this tissue you get bone marrow derived cells. So these are immune cells in green, they come first, and then cancer comes later. So the red dots here are cancer cells, and they settle right there where the immune cells are already present. And then looking at the cell count here, you see the first arrival of the green cells, and then later arrival of the red cells. Which indicates that the immune cells have something to do with the arrival of the cancer. And then looking through the literature, there's many more incidences where this has been observed. Immune-mediated epithelial to mesenchymal transition, immune cell promotion of metastasis, immune regulation of metastasis, bone metastasis. I mean, bone is the home of immune cells, right? That's where the immune cells come from. So maybe one explanation to have metastasis in the bone so often is that this is where the immune cells are, and maybe they actually help the process. Virus infections have been related to metastasis because they also lead to immune response. Okay, how does this effect work? Let's look a little bit on it in a detail. I talked about macrophages earlier just a bit. They can have phenotypes M1, M2, and also everything in between. So this is a continuum of phenotypes. M2 promote tumor growth. They promote angiogenesis. They promote motility, and they promote metastasis. Whereas M1, they fight the cancer. T lymphocytes. They're effector T cells which kill the cancer, and regulatory T cells which stop the effector T cells. So indirectly working for the cancer. Platelets. Platelets produce growth factors. So platelets play a role in the blood system. And they protect circulating cancer cell clusters by just going around them and building like a protective shield around the circulating cancer cell clusters. And then tumor-associated fibroblasts, they release growth factors, they help with structural integrity, and they also induce angiogenesis, so blood supply to the cancer. So it seems like we are in a bad cop, a good cop situation. So the immune system is supposed to be good and help us fight the cancer, but then it can be compromised and work in favor of the cancer and against the body. Okay. So let's analyze this with mathematical modeling. The model we are using is a system of 8 ODEs. I'll show you in a second. And we can analyze it in 3 stages. So we reduce it to 3 ODEs. And in this case, we can do a full bifurcation analysis and also full parameter fitting to data that we have. And then in stage 3, we reduce everything to 1 ODE. And that made me very happy because I can analyze 1 ODE. And actually, we can really learn something from this 1 ODE for the entire system. This is done using singular perturbation, reduction on a slow manifold, and I show you some of the details in a second. Okay, let me first show you the 8 ODE model. We have 2 compartments, primary and secondary. UI is the tumor cell density, VI is the necrotic cell density, XI are the cytotoxic immune cells, so those ones which kill the cancer, YI are the tumor-educated pro-tumor immune cells. And then, yeah, what do you expect, right? So then you get a system of 8 ODEs, and all these terms have meaning. And I'm definitely not going to go through all these terms one by one. maybe I show you one term here, maybe this one, the education term. So the XI are the cytotoxic immune cells. And then by the presence of the tumor, which is U, they are then educated and they become tumor educated cells. So the Y is right here. Okay, and then of course the question is, how do you model this education rate at 1 of U1? Another aspect which I like to highlight maybe is the growth rate factor. Okay, so now the Y is the tumor promoting immune system, and this increases the growth rate for the cancer, for example, by releasing growth factors or by inducing angiogenesis. And of course then, all the other terms have the meaning they have. Okay. So this in total gives about 70 parameters, which is way too much. We can estimate about 40 from the literature, which means 30 unknowns. And so we are stuck with a more theoretical analysis. So we can still theoretically analyze what's happening is here, but this is too much unknowns to really do a fitting to data. But one result we have is the results by Kaplan from 2005. I've shown you this graph before, where the bone marrow derived cells arrive early and the tumor cells arrive later. And we can have the same effect down here, which is a model where the immune cells come early and then the tumor comes later. Okay. Yeah, so now the thing of the primary resection, this is really interesting. Now we're only looking at the secondary side, and then we remove the primary at a certain time. The black line here is a time course of the metastasis if you leave everything alone, you do no surgery and nothing. Time on x-axis and number of cells in log scale on the y. But then if you do resection early, like here at this time point, then you follow the green curve and the metastasis dies. So the primary is removed and the metastasis dies. Everything is good. If you remove the primary later, like here in the red curve, then the primary is gone, but the metastasis still grows. Okay, and it grows essentially the same height as it would have grown before. And so what you see is a sharp transition between the green and the red. So if you remove the primary early enough, you can also control the metastasis. If you remove it too late, then actually the metastasis will still grow. Okay. Now, playing on the parameters, you can also then generate some time of dormancy. You see the time axis is in days. So here the blue bar is between, what is it? It's about, 300 days. So it's about a year or so. So you can easily generate a dormancy of a year or longer, depending on the parameter values. Okay. Here is the relation to immunotherapy. So in immunotherapy, the idea is you take immune cells from the tumor environment outside of the body, and then you multiply them, and you also increase their fitness, and then you reinsert them into the body, and you hope that these new immune cells help to fight the cancer. And this is the case up to a limit. So what is shown here in this graph, again, time in days, you see the growth of the secondary cancer. Again, the dashed line is with no treatment, then you just get a growing metastasis after about 250 days. But then if you increase a dosage of immune cells, you can delay the growth. So if we go to the right, we increase the dose of the immune therapy and we delay the growth of the cancer by 40 days, 50 days or so. But then it turns around. So if you further increase the dose, it turns, and then you get, again, earlier disease, even though you have increased the dosage. And this is a case where then you turn good cops into bad cops enough so that you get a negative effect, right? So the new immune cells which you put into the body, they can also be educated to become pro-tumor, and at some point they might actually help. Okay. Here's an experiment for metastasis at the site of injury. So here's a primary tumor which grows here to its carrying capacity. And then once it has grown, we insert an injury at this time. And you see after a while, it's only 100 days later or so, we get a metastasis right there where the injury happened. So we're kind of triggering a local immune response, which then educates immune cells and then helps the cancer to settle. All right. So let's do a little bit more fun with math and maybe get even more understanding of this system. So here I reduce it to 3 equations, where I now focus U to be the tumor cells at the secondary site, X the cytotoxic immune cells, Y the tumor-educated immune cells only on the secondary site, and then you get a system of 3 equations. Fine. But then we can look at these scales, and the tumor dynamics are slow. The immune dynamics are fast. So we have a system where the immune equations have an epsilon in the time here. So we have 2 time scales. And then we can do a singular perturbation analysis, and we can show that the dynamics reduces to a slow manifold. And the slow manifold is given here. And the slow manifold is G1 is 0 and G2 is 0 in a 3-dimensional phase plane. So this means G1 is 0 is a plane, and G2 is 0 is a plane. And so where these 2 planes intersect, this is where we have a slow manifold. And this is what is shown here. So this picture is essentially incomprehensible. So somehow you're intersecting the blue plane with the red plane, and where they intersect, you get the green line, and the green line is a slow manifold M. And so here we just take it out, and so then the red line here in this graph is a slow manifold. And then we compare that with a solution. A typical solution then very quickly goes onto the slow manifold, and then it lives very, very close to the slow manifold, as it should. Okay, so now we have reduced the system to a 1D system, but it lives on a curved thingy here. But how does it look like? So let's come back to the primary resection. You have seen this picture before for the 8-dimensional system. Now it's shown for the 1-dimensional reduction. But the behavior is the same. If you do primary resection early, you get the green curves and the patient survives. If you do it later, you get the red curves and the metastases grow. But now we can understand this wonderfully using our manifold thing. So here, the dashed line is the slow manifold in presence of the primary tumor. And so you get dynamics which goes very close to this black dashed line. But then upon removal, you fall down onto the other manifold, onto this one, where there's no primary tumor. And now it depends where you fall. So the green curves, you fall early and you go back down here, no metastasis. The red curves fall down a little bit later and you come to the cancer state. And what you see here then is a settle point, or in 1D, it's an unstable node, which divides those 2 cases. So if you fall down earlier, you go down. If you fall down late, you go there. And then on the manifolds, you can look at the phase plot, and you see you get an additional equilibrium point right here. So then they go there and they go there. So you get a very nice understanding of how this transition happens. Okay. For metastatic blow-up, there were a few theories which were discussed, which I like to mention just quickly as well. So metastatic blow-up, again, is a case when the primary tumor is removed and then the metastasis grows. And one theory could be resource monopolization, so that the primary tumor uses up a certain resource, maybe oxygen, maybe phosphorus, maybe some nutrient, so that the metastatic cancer has no supply and cannot grow. Another one would be immune surveillance, so that the primary tumor creates such a strong wound and a strong immune response that just as a shadow effect, the immune system would also control the metastasis. Makes a lot of sense. Local promotion, global inhibition. Also, people were looking for chemokines which locally promote growth and globally inhibit growth. A little bit the idea of a Turing kind of pattern, long-range inhibition. But these were not identified, I think. I think this is still a theory, whereas these ones actually do work. And then there's the immune-mediated therapy theory of metastasis, which I just presented in our model. And so if we look at what they can do, so the theories 1, 2, 3, 4, yeah, they can all explain these two things. But as soon as the immune system plays a role, then we have to rely on the immune-mediated theory for metastasis. Okay, so I have a few more minutes. So there's one little detail which is interesting to think about, and I'm not quite sure what the consequences really mean. And this is biopsies. So in many cases, cancer patients undergo a biopsy, right? The clinician takes a sample tissue, a tissue sample, and then looks at it under a microscope and then see, is this cancer or not? But then this biopsy creates a little wound, a micro wound in the tissue. And then this wound stimulates the immune response. And then the immune cells come in. And then these immune cells could maybe be educated to become bad immune cells. And then this might actually help the cancer to grow. So the question is, can biopsies help the cancer to grow? And if this would be the case, this would be not good. So here's a paper in this direction. Preventing inflammation inhibits biopsy-mediated changes in tumor cell behavior. So they talk about biopsy-mediated cancer growth. And this could be prevented by reducing the inflammation level. And here's another one. Acute inflammation induces by biopsy in mouse memory tumors promotes the development of metastasis. Ouch. So this is really bad. And the key here is acute. So in these experiments, the biopsies are half surgeries. So they're not taking a little sample, they're taking a big sample, creating big inflammation, which then helps development of metastasis. Okay, and then there's another very important statement by the Mayo research team, Mayo Clinic in Arizona. They find biopsies do not promote cancer spread. And this should be made very clear for people in this situation. Biopsies are super important and super useful because they help to identify the disease. And then the best treatment can be found often based on the biopsy. So whatever I say, do not tell your, I don't know, relatives, whoever's in the situation, that biopsies are bad. Biopsies are really good and they should be done. But what does our model say to this? So here's our modeling result. And look at this green, blue, reddish thing here. Phi is, what is phi? I should have written down what phi is. Oh yeah, phi is the supply. Phi is the supply. No, phi is a shedding from the primary. Phi is a shedding from the primary. So it's a supply of new cancer cells into the metastatic system. And then here we have an inflammation level, which is then induced maybe through a biopsy. And we get a blow up or growth through biopsy only here in this little blue wedge. Okay, so what this means is in the green area, let's say if we have a small biopsy, maybe on this level, then we keep a small metastatic tumor. It doesn't do anything to the metastasis. Here in the red area, in this bit, we get a large metastasis no matter what, if we do biopsy or not. And so only here in this blue wedge, the biopsy can in fact initiate metastatic growth. But this is for a very high inflammation level. Like I said in the mouse paper earlier, for a very acute inflammation, this effect is indeed possible. But for realistic levels of biopsies, this is actually not possible. Okay, so then let me summarize. I talked a lot about lots of things. The first bit, I had a branching process with settlement to see where metastases go. And this led directly to the metastatic reproduction number. We fitted it to mice experiment, but it would be good to also use it in context of humans, which we haven't done. Then in the second part, I looked at the pro-tumor effects of the immune system. And including the pro-tumor effects, you can all of a sudden explain all these strange observations of metastasis, blow up and injuries and immunotherapies and so on. Now, how the education works, how tumor cells influence the immune system and change their phenotype is very much unknown, and more research is needed, and also more research is done in this direction. Okay. Including the tumor education, we can explain all these effects in one model. But some of these effects have been modeled in isolation, but now we have one model which can do all of this. And I think this would have not been possible without mathematical modeling. So I think here's an example where we can gain insights from mathematics, which we wouldn't have gotten otherwise. Well, that's just my opinion. Okay. However, the details of the pro-tumor immune effects are different from cancer to cancer and from patient to patient, right? And so this is not a one-fits-all approach. And we would need a patient-specific use of this model. We need a genetic fingerprint of the cancer and also a genetic fingerprint of the immune system. And I think only if we have this together, then we can really make informed decisions about this. Yeah, okay, so that's the end of my talk. Here are the relevant papers, and I thank you very much.
Thank you for the nice talk. It's very interesting. Okay, we have now time to some question, or you can yourself or via the chat to propose your question.
Okay, there are no questions so far. I would like to ask you, Thomas, about the resection of the primary. So your results indicate that there is a certain point after which there's no turning back, essentially. And my question would be, since we don't know in a clinical situation, we don't know what is the timing, the zero time to start with. We don't know if we are before or after that critical threshold, so to speak. So the issue would be, it would be maybe even better not to remove the primary in case we are not sure that it is already late to remove it, or not at all.
Yeah, that's a good question. Let me just jump back to my earlier slides. So one consequence is, of course, as early as you can, right? So you shouldn't wait another 6 weeks or so before you treat a patient. But also here, the black curve is the untreated case. That's the control. So if you do nothing, you are still worse. Okay. So the red curves go up, but they go up later, times 10 to the 4 days. So quite a bit later.
Okay, okay. So you gain something, yes.
You still gain something there.
Okay. Thank you.
I have a question. May I put it?
Yeah, okay.
So I just want something is a question about the biology, but which definitely can have interesting implication in mathematics. Can you just teach me a little more about the M1 and M2? Are they the same kind of cells which are modified by communications between tumor and macrophages, or are effectively different type of cells of macrophages, I mean?
Okay, yeah. So I don't think I know enough about this. So they're definitely macrophages, so they're the same cell type, but this is a different phenotype. So and they can also switch one behavior directly from M1 to M2 or everything in between.
Yeah, that was the answer I was.
Oh, I see. Okay, yeah.
Yes, thank you, thank you.
We have a question by Francesco Cavalleri. So if you want to ask it by yourself, please open your mic.
Thank you. Good morning. Thank you for the talk. Very interesting.
Thank you.
I can't understand in the very first model, the stochastic model, in the equation, what are the Q, the xt term here.
So, somewhere here? Okay. Yeah.
Yes, Q and P, I didn't catch what are.
Oh, and I didn't tell you. So these functions Q and P, they are very different depending if you use big F, big V, big H, or big Q. It's written out in the paper, but I didn't show it here. And I don't have it at the tip of my fingers to show it now.
Okay.
Yeah, sorry, I need to refer you to the paper.
Thank you.
So I have a question.
Andreas?
Yeah, okay, thank you. So an important diagnostic tool today is liquid biopsy for finding out metastasis formation. Your model is more or less an ODE, no?
Yes.
There is no spatial component. Could you have those fraction of the cells which can be diagnosed by liquid biopsy, or can you get any hint how much of the cells will be diagnosable via the liquid biopsy?
So liquid biopsy, you mean from the blood, right?
Yes.
Yeah. So we have a primary and a secondary tumor site, and we have transfer terms between these tumor sites. And this kind of models the blood system. So we could say a biopsy measures whatever transfers from one compartment to the other.
So it would be the sum of both fractions, which I diagnose in the blood. One would not be able to distinguish the source. Probably.
No one would. It depends a little bit on the question we are asking. But what I'm thinking is about the transition terms.
Okay.
Now, which ones? Where's my pen? Here's my pen. It would be the shedding, S1U1, and then where does it come back? And then the establishment in the secondary side.
Okay.
There's the S1U1 as well. So it would be this term you would be looking at.
The shedded cells. Okay.
Yeah.
Thank you.
Thank you too.
Okay, we have a couple of questions in the chat. So first we have Mahish Mathi. Shall I read it out, or would you like to open your microphone? Okay, so it's asking about the immune system of model organisms like mice, which are depleted in order for tumors to settle in the body. And the question is, how reliable would be the results obtained using such model organisms? And then, shall we change this practice?
This is a very good question. Thank you very much. Yeah. And I think through mathematical modeling, we can actually save many mice or other organs. I mean, I think a certain level of animal experiments is always needed. But as I said, the parameter values for my metastatic research are completely off. They have absolutely nothing to do with the human situation. And maybe informed modeling like we do here can actually help to gain insight as well.
Okay. Then there is Elena Torres. Elena, would you like to?
Thanks for the talk. First, I would like to know if the two models, the stochastic one and the immune system one, are connected, or if they are independent models.
Are you looking for a new research project? So so far they're indeed independent. They have been done with different students. That's the one thing, and the idea was to put them together at a later point, but we haven't done it yet. But of course, yeah, you're right. It would be interesting to see the spatial dependence and also the immune system dependence. Actually, one thing for the spatial model is, I didn't really mention it too much, is the settlement. We should make it dependent on the organ. So we should have a settlement rate for the bones, a settlement rate for the liver, a settlement rate for the lung, and look how the different organs interact. So I think that would be a natural next question for the spatial model.
There's another question in the same line in the chat. Well, essentially, they are asking if the models are generic or you have to tune in specifically for the different types of tumor.
They're actually very generic. So these results which I showed are very typical for a wide range of parameter values.
All right.
I have a question also. You mentioned, for example, here in this slide, that the tumor education. For example, in connection with the question of Nino, tumor sometimes provokes macrophages to go there to activate TGF, that in fact is an anti-tumor immuno proteins. But because there is a level in which is bad for the tumor, but this is a high level, it is very good for the tumor. They take advantage of this excess of TGF. This is a kind of tumor education that you refer, or there is this can be included in that?
Oh, absolutely, yeah. This is exactly what we had in mind. It's actually still on the slide, right? So they release a growth factor, and so then this would increase the growth rate for the cancer as well. So that's one of the effects we have in mind. Yeah.
Thank
you. Maybe we can consider a final question by Kevin Spinici. Would you like to ask it yourself? Else I will read it out.
Yes, I wanted to know if you can talk a little more about how you reduced your model with 8 ODs to 1, and also the impact of the result by such a reduction.
Yeah, so when we do model reduction, we always try to keep the typical behavior and get rid of all the kind of unnecessary details. So just roughly, this here is all the primary tumor, these 4 equations. And in this reduction, we assume the primary is well established, is just sitting there, slowly growing. And so we use the primary as an input to the secondary. So that saves already 4 equations. And then for the secondary, we remove the necrotic cells, this one, because the role of the necrotic cells is to stimulate the immune response. So the cancer cells grow. When they die, they become necrotic, and this stimulates the immune response. So we shortcut this, and we just say the cancer cells stimulate the immune response directly. And so then we are down to 3 equations. And I wish I could change the color of my pen here. Oh yeah, there. Let's go with black. And then these are fast. So now if you look at the parameter values for the immune dynamics is fast. It responds within hours. Whereas the cancer growth, so this is the other remaining equation, is slow. Cancer grows on the timescales of days or weeks or months or years or super slow. So you can do a fast, slow analysis. You assume this is in quasi-steady state. You set the time derivative is equal to 0. And then what you get here defines the slow manifold. And then you have a dynamical equation. So the only equation is really this one, which remains. This is the one ODE that remains, but it lives on the slow manifold given by these 2 equations down here. So lots of errors are my thing, but I hope that helps to get the idea of what's happening there.
And about the impact of on the result, is there any impact of the reliability of the result?
Oh, definitely, yeah, there would be.
Okay.
Yeah, as I say, we try to find to identify the typical behavior, but this is all based on assumptions. So each of the arrows I drew has a scaling assumption. It has a quasi-steady state assumption. If these assumptions are wrong, then this does not hold.
Okay, thank you very much.
Thank you.
Maybe one very last question by Elena Torres again. Elena.
Yes, I have read somewhere that if you have an autoimmune disease, that increase the risk that you have cancer. Is that related to the immune-mediated theory of metastasis?
I would think this is more related to the direct effect of the immune system. So this should also be made clear that the human body develops many cancers, and then they are killed immediately by the immune system, and nobody sees them and nobody knows. So people in my age class, I'm now 55, do have cancers somewhere already waiting, and hopefully, I think most of them will be really controlled by the immune system right away. And only if things go wrong, then the cancer develops further. So which means immune compromised people might actually develop it quicker just because the immune system is compromised.
All right, thank you, Thomas. So if there's no more questions, I would like to thank you again for this insightful and very interesting talk. Actually, you leave us with more questions than answers, I would say, in the long term, but
which is good, which is all right.
See what we can do collectively about that, but still. So thank you again. Thank you, everybody, for being here. Let me just briefly remind you that next week we will have Andreas talking, and his talk will be actually related. He will address the cancer dynamics from the perspective of collective effects. And we will meet you hopefully same day, same hour next week. So thank you very much.
Thank you.
Thank you, Thomas.